divide this by, yeah, n-1. And this is the standard deviation, where S is equal to the standard deviation. It's not so easy to write with this but I think you can read it. Okay, standard deviation. Okay, and then when we have calculated the standard deviation and the average, what remains is the confidence interval. How confident are we that we engulf this average, so that we can say with some certainty that this is a true value. And we have a definition for confidence interval, which is interpreted in this way. And here, the mu here, it's the true value, the value of the population. If we had done, for example, 1,000, 2,000, or many measurements, then we will come close to the true value. This is the mu. And this is our average which we got from here. And then T is a value which you get from the student's T distribution, based on how on the significance level. If we choose, for example, 95%, I'm confident that the true value is between these values. You can also interpret this like this, and it can make more sense. This is lower than this, but it is higher than this. That's what this means. So the true value is between these two values here. And then this is a confidence interval, and then we are going to look into how to comparison of a one average. That is this average, yeah, with a reference value, or we can say reference known value. These reference materials, you can buy them from the National Bureau of Standards, for example. We have different types of reference materials depending on what we are analyzing, and these reference materials are certified, meaning that it contains, for example, this much arsenic. If it's rice which is certified, then it's labeled, this contains this much of arsenic. And then we do the measurement, and then if we come close to these values, then we are satisfied. If not, then we must have to do more measurements or to refine our analytical method. And then we have another comparison also, which is comparison of two sample means. You don't have certified reference materials for all chemical compounds. So if that is not available, then what you do is that you compare your new method. For example, if you are doing with method development, then you compare your new method with a well-established method. For example, in analytical chemistry, we can talk about atomic absorption spectrometry, and then we can compare it with anodic stripping voltammetry, electrochemistry for analysis of metals. And the atomic absorption spectrometry or inductively coupled plasma, we have spectroscopic methods. That method is well established. And then if I am developing an electrochemical method for analysis of a metal, let's say copper or cadmium, then I just compare the results I get with the well-established and then with the one which I am developing. So we are going to look on this type of comparison as well. And then we have a third one, which is called pair t-test. And then we are going to see why we need to pair. Why can't we do it this way, the second way? This is the first, and the second, and the third. So then if we have more time, then we are going to look also into linear regression. In linear regression, what we do is that we establish an external calibration curve, and we measure on our sample, and then we go into the calibration curve with our signal, and then evaluate the concentration that way. And this assumes that the external calibration curve or the standard solutions which we have prepared will behave in the same way as our chemical compound in our sample. But that is not true all the time, because the chemical compound in your sample may contain a matrix which can make it difficult to evaluate the concentration of the analyte of the chemical compound which we are interested in. So yeah, why so? Because we can change the sample integrity, for example, during sample workup. Or the instrument may not work well, we may fail in calibrating and so on. So we will talk about linear regression using external calibration curve and then standard addition method. And then this is the external calibration curve calibration. And then we are going to talk about standard addition. Standard. Why do we need to do standard addition? And which one is better? So that will be, this is just a summary of what is going to come. So I will go to my lecture notes, to my slides. Okay, so we switch this. Okay. Okay. Do you see my slide?
Yes, yes, we see them.
Good, nice. So again, just to repeat, why should chemists care about statistics? Not only chemists, but it can be biologists or any science where we do measurements and collect data. So to find answer to the questions one poses, measurements are done in all experimental research. And when the same measurement is repeated a number of times, the collected data shows variability. Despite this, we must have to draw a conclusion from the repeated measurements. And if we use a correct, appropriate statistical method, then we can come close to the true value or to convergence. Warning here, if silly questions are posed, of course, the answer will also be silly. Therefore, should statistics never be a substitute for an intelligent critical thinking? So if you fail in the sample preparation or somewhere from collecting the sample, bringing it to the lab and storing it in a refrigerator, and then take it from the refrigerator, maybe one time or two times, thawing, as we call it. This can, of course, in some cases, alter the integrity of the sample or the analyte which we are going to look at, and this cannot be corrected by statistics. Of course, we can see if something is changing with time and so on, but solely statistics cannot solve our problems. So we must have to know the subject or what we are doing. But the combination of statistics and the knowledge in the subject is important. Okay. And there are sources of difficulty confronting the investigator. One example is the confusion of correlation with causation. Whenever we have a plot that shows linear relationship between a signal, some sort of a signal, and a variable on the x-axis, so it's easy to say that this is increasing due to the increase of, in this case, the number of storks increases and the population increase also in Oldenburg. And then we can draw a conclusion that thanks to the number of storks that increases, the population is increasing in Oldenburg. This is a confusion of correlation and causation. And a third parameter which is hiding here is the time. This is measured, I think it was again as a number of storks observed in that year, per year at the end of each year. So a third parameter is hiding here, which is time. So we must have to be very careful when we interpret this type of correlations. So although few would be led to hypothesize that the increased number of storks caused the observed increase in population, investigators are sometimes guilty of this kind of mistake in other contexts. So what we are going to focus now here is experimental error, which can be systematic, it can be random. Systematic errors, that's an error that can be coupled to a special cause, known or unknown. For example, if we have a pipette, which should pipette 10 milliliters, and then if we have a bubble there, then the volume will not be 10 milliliters, it will be less. So we have some sort of systematic error there. But random error, it's an error which we cannot keep in control. And systematic error, most of the time, it's unidirectional. Let me see if I can put here. Okay. Let's see that. Yeah, you can get, for example, increase all the time, then it's or decrease your results. So it doesn't pan back and forth like this. If it pans back and forth, then it means that you have a random variation. But if it declines all the time or increases, then you can suspect that you have some sort of systematic error in your measurement. For example, weighing hygroscopic sample, positive error, irreversible absorption in chromatography, negative error. Chromatography is a sort of separation method. Maybe most of you maybe are well acquainted with that. You have liquid chromatography and gas chromatography. And we have a stationary phase which will interact with the sample. And if it interacts with the sample irreversibly, then it will keep the sample or the sample components, and then they will not come out in a reasonable time. Then you have a negative error that way. And random error is often caused by a number of variables that cannot be kept under control. And each variable contributes a small error, and the error switches to both sides. You can say, it can switch like this, for example. Example here, variation in temperature, variation in humidity, sorry, variation in electronic noise. Sorry. And the merit of the experiment is expressed using accuracy and precision. And as I told you, accuracy has to do with the nearness to the true value, and precision is the reproducibility of the measurements. We can compare this with, for example, if you throw dart. Let's say maybe we have 20 there, and then 1 and 5. And let's assume that we are aiming at 20. Let me see. I can change the color. Yeah. 20 and 1 scores, 2 persons are, for example, competing with each other. And one scores like this, 3-1, and the other one, we have them there. All three there. And remember that we are aiming at 20. So which one is better, the green one or the black one? Our aim is 20. So we have at least one score on 20. So the accuracy is better for the black, but the precision is better for the green, but accuracy is not good. So we are far from the target, but we can reproduce the signal. So we have all the result. This means that we have some sort of systematic error, for example. That can be the reason why we have this deviation from the true value. So you must have to be able to differentiate, to distinguish between precision and accuracy. So random error influences nearly almost the precision if the measurement is repeated a sufficient number of times. The accuracy in a measurement is usually influenced by a systematic error. So here we have an example, probability distribution, determination of lead. We repeat this a number of times, the measurement. We have 10 values here. And our eyes can easily extract information from a dot diagram like this, which is down here, but not from a table, for example. This is on a line, but let's say if we had 50 or 100 measurements, then we will have a table. So it's not so easy to extract information from that table. But for, let's say, values 10 measurements up to 15 measurements, for example, you can have a dot diagram. And this will show you if, for example, one of the values is an outlier or not. For example, this is a little bit farther, and then this can be a little bit far, but these are, yeah, more or less, yeah, not so big difference between them, but there's bigger difference between this point and this point to this group of measurements here. So there are test methods where we can check if one of the points is an outlier or not. So you cannot just simply take out one data or one result. You must have to be able to check if that is statistically different value or not. So we have some sort of test for outliers, which is based on R test or Q test and so on. We will see some examples on that. So when a large number of, as I said, the dot diagram is a valuable device for displaying the distribution of a small body of data up to 20. But when a large number of results is available, then the dots become hard to distinguish from each other, and we are better able to appreciate the data by constructing a frequency distribution. This is what we call a distribution, frequency distribution. What we have here is values between, let's say, 56 and 57 here. Let's see, I can use the laser pointer here. Values between 56 and 57, 3 values there, yeah. And then between 57 and 58, around 9, and 58 and 59, around 20, and 59 to 60, around 45 results. And the probability of having the true value between 60 and 70 is represented by the shaded part, by the area of this shaded part. So if the measurements are made more, I mean, if we have thousands of measurements, then these bumpings will be smaller, then you will have more Gaussian distribution. That's what we will see in the next slide there. So the horizontal axis is divided into segments corresponding to the range of groups. And on each segment, a rectangle is constructed where the area is proportional to the frequency in that group. So as you see here, if you do more measurements, then the curve will be more Gaussian. And the probability of finding the answer between 60 and 70 is represented by this shaded part. Okay. And this is just what I had on the whiteboard. The mean of a population. You just add all the individual values and then divide by the number of measurements done. spreading in a population, and this is what we call the standard deviation in a population. The difference between this one and for a sample is that you divide by n-1 instead of n. And that's what you will see here. So this is our formula for standard deviation calculation. And the average there. And degrees of freedom, I don't know if I have time, but you can show why you need to subtract 1 from the number of measurements done, because if you have 4 or 5 measurements, for example, then you will be left by 3 degrees of freedom. What this means is, let's say if we have, I can pen. Let's say that we have okay. If we have values like 30, 27, 28, 31, 29, 32, 33, for example. If you take the average for this, then the average will be equal to 30. So if you subtract the average from each, this is 0, and then this is -3, and so on. So the sum here will be equal to 0. The sum of all these differences will be equal to 0. And this will mean that if I calculate the average, and then knowing that the sum of all the differences is equal to 0, then I can calculate one of these, if one of these values was missing, for example, then I can calculate it based on the average which I have calculated. So I lose 1 degree of freedom because I have calculated the average. From the average, I can deduce the missing value, for example, from the average, and knowing that all the differences, the sum of the differences is equal to 0. This will enable me to calculate one of the missing values. So that's why we subtract 1. So number of degrees of freedom, n minus number of parameters calculated before the calculation of S. And the number of parameters here, it's the average. As we will see then for calculation of standard deviation in a calibration curve, then you have n-2 instead of n-1, because for the calculation of the centroid, then you need the average of X and the average of Y. We will come back to that. Okay, so here is just the summary of what we have talked about: population and sample, some definitions. And I can send this presentation also later on to you if you need it.
Yes, it will be great. Thank you.
Yeah. And combined error. Combined error is like if you have, let's say, if you have only one value, let's say we are measuring concentration of copper or nickel using atomic absorption spectrometry, then we can get maybe 30 ppb and 29 ppb, 31 ppb, 27, 28, and so on. So here, then we can calculate the average and then the standard deviation. Now, if we are asked to calculate, let's say, the concentration of lead in a sample, and then we take a pipette, and then using this pipette, this is 100 milliliter, let's say 100 milliliter of measuring flask, and then the pipette is 10 milliliter. And then we take 10 milliliter from here and then put it there. And then we titrate using EDTA, for example. And this EDTA must have also to be standardized before, meaning that you have standard deviation here also. So the EDTA concentration is not exactly 20 millimolar, for example. It can be 20 plus minus 3 millimolar and so on. And then the 10 milliliter is also not exactly 10 milliliter. It can be 10 plus minus 2 milliliter. And then the 100 milliliter is not 100 milliliter either. You have standard deviation. So now, how do I calculate the standard deviation for let's say, the number of moles of EDTA in a titration, for example, is equal to the number of moles of lead. And the number of moles of EDTA is equal to concentration of EDTA times volume of EDTA, and concentration of lead times volume of lead. And then what we want to do is to calculate the PB, the concentration of PB. Then this is equal to EDTA times volume of EDTA. This is times, and then divided by volume of PB. So remember, this is average. So to all averages, we have standard deviation. So the question now is, what will be the standard deviation of this one? How do I calculate the standard deviation? So in this case, what you do is that you take the standard deviation for this one divided by, yeah, that's what you have here. And it will be standard deviation for concentration of PB divided by PB is equal to, yeah, standard deviation for the calculation of concentration of EDTA divided by that, and then you see how it is. Yeah, so this is just an example represented by taking A, B, C, but you can call this A, and then this B, and then this C, for example. Okay, that is how we calculate the combined error. And then we have the normal distribution, which is very useful in statistics, this Gaussian normal distribution. That's what we assume that we have. And we have an example here, control of the air quality in a working place with respect to the concentration of, for example, carbon monoxide. And the determination gave concentration of 25 ppm. We did only one measurement, so that's not enough. According to a list from Occupational Health Authority, the concentration should not exceed 35. So the question is, can I, as an analytical chemist, be confident to say that the air quality is good considering carbon monoxide by doing only one measurement? No, I need to do a number of measurements. Before doing the experiments, then we must have to eliminate all sources of systematic error, meaning that we must have to calibrate the instrument and so on, draw a plot diagram and see how your results are distributed. And this is an example of that. Here, let me see. All right. And variation of data is defined using models. That's a normal distribution that we use here. And in the confidence interval, if we choose plus minus 1 standard deviation, then it will represent 68% of the Gaussian curve. And most often, if nothing is said, we used to use 95% confidence interval. And then if it's 99.7%, then you will have plus minus 3 standard deviations. Then the more you open, then the more will be the standard deviation. Okay, so confidence interval, again, that's what I had at the beginning. So confidence interval is represented by what you saw in the whiteboard. Yeah, that's what I had there. It will come here. Here it is. This is for the sample. And that's what I had on the whiteboard. This is average, the students' T distribution, and the standard deviation, and number of measurements. Now maybe I need to rush. Do I have only 5 minutes? Is that the case? Do you hear me?
Yes.
Yes, we hear you. It's okay with the time. You may go on.
Yeah, can I go for 10, another 10 minutes?
No, you have more minutes. We
Yeah,
have
okay.
more than half an hour for the
Oh,
next
okay.
lecture, so you may speak as long as it takes. It's okay.
Nice. Then okay. Very good. I thought that it was 45 minutes, so that's but I can keep on talking now. It's good. This is a student's T distribution. Let's say that if we have 10 measurements, then the degrees of freedom will be 10 minus 1, because most often we calculate the average, and then we lose 1 degree of freedom, then 9. Now, okay, this is already degrees of freedom, so you don't need to subtract. This is not number of, in some tables, it's the number of measurements, but here it's a degrees of freedom, so the 1 is already subtracted. So degrees of freedom 10 and 95% confidence interval. Then we have 2.131. And what we do then is just plug in this value here. Let me see. We plug in that value here. And S is the standard deviation, and N is the number of measurements which we did, and this is our average. Let me see. And now we can continue there. And test for outlier. Test for outlier, you have different ways of doing test of outlier. Test for outlier. This is Grubb's test. You have the questionable value and then minus the average, including all the questionable value, of course. If you have 10 measurements, for example, then all the 10, the average of the 10 measurements, and then the standard deviation. So if the calculated value exceeds the critical value, then the suspected value is rejected. And here is a table for the Grubb's test. So if we have 10 measurements, and then if we have a value which is greater than 2.176, then we can reject it. And we have one example here. The following values were obtained from a titration. That is a titration of HCl with sodium hydroxide, for example. Then you have 0.05, 0.043, 0.076. Then we take the average and the standard deviation. So the question now is, before doing that, is 0.076 an outlier, or should I include it, or should I exclude it? So the average is 0.056, and the standard deviation is 0.017 for all three values. And the G, that is the G value, is 1.176. And G table from here, you can see here is 1.153. So the question is this an outlier or not? So as you see here, it's not so big difference, and the number of measurements which we have done is only 3. So in this case, then what we do is that we do more measurements, like 5, 6 or more, 10 measurements to be sure if it is close. So you can say that this is doubtful, do more measurements for verification. But normally, if the value is higher, then we can exclude it. And alternative expressions for testing outliers. This is R test, and then we have Q test. They function in the same way, but we have different tables for R test and Q test. So M minus X divided by S. M is the average, X is a suspected value, and S is the overall standard deviation. And here, likewise, suspected value minus nearest value. So they will lead us to the same conclusion, but we have different ways of testing outlier. Okay, then this is, I think, for my students here in analytical chemistry, this used to be, I use also to pinpoint, this is one of the important parts, that is significance test. And here, I think it's better to go to the whiteboard. I can come back here. Let me see. Right. Oh, okay. Significance test. And now we can go through the first one. The first one is a comparison of a sample mean with a reference value, and this reference is just a certificate value or known value. So let's assume that we have developed a new method for analysis of metals, and there is a well-established method, another method available in the lab. So we can do that comparison using these two methods. But now here, the comparison is based on analysis of a reference material. So we use the reference material. The reference material can be bovine leather, for example. We can analyze the content of lead in that sample. It can be arsenic in rice. Then you calculate the concentration of arsenic using your method, and then compare the value which you get with the certificate value. So here we use the interpretation for the confidence interval, where S is standard deviation, number of measurements, T is the student's T distribution, average, and confidence, the true value here. So we can rewrite this like this. S T calculated. Oh, sorry. So what we do now is that we subtract the average, which we have calculated using 5 or 6 measurements, and then this is a true value from the reference for the reference material from the certificate. We buy this reference material, and then with that reference material, we have a certificate. This reference material contains this amount of arsenic, for example. And then we put that value here. This is our value, and then this is the number of measurements which we have, which I have. The number of measurements which I have made, and this is the standard deviation. Okay, so if T-calc is greater than T-table, that's if it is 5 measurements, then you go for 4 degrees of freedom, and then from that table which you saw earlier. And then if this value is higher, then there is difference. There is difference. But if it is lower, then it's okay. So there is difference. What does this mean? The result which I get using my method does not give me the same value as the certificate value. So now I have compared my method and using a reference material, then I can check if I get good result on it. This is one way. Another way is, you see, next, and this is comparison of 2 sample means. And here it can be, for example, method 1, which is based on atomic absorption spectrometry, or it can be also inductively coupled plasma, ICP-MS, mass spectrometry. And here it can be electrochemical measure, anodic stripping voltammetry for metal analysis. Let's assume that we are measuring copper in water in environmental sample. So we get these values, x2, x3, x4, x5, and so on. Then we have the average here, and the standard deviation. And here also we have x1, x2, x3. We make a number of measurements here. Also, the number of measurements that don't need to be exactly the same. We can have, for example, fewer measurements here because the ICP-MS, it works with argon and it can be a little expensive. So maybe you do only 5 or 6 measurements, but here you can do more measurements. And assume also that this one is the well-established method, the conventional method. And this is the new method which you are developing, electrochemical method. We can call this, for example, x1. Then we can call this x2 and then s2. So now the question is, how do I compare this averages? So to do that, first what we need to do is to check how different or how similar the variations or the spread of the data is. So if this is, let's say, x1 average, and this is x2, so there is a difference here. But to check this, what we need to do is that we must have to check the variance first. So we do f-test first, f-test first to compare the variances. And then this is done by f is equal to s1 to the power of 2, s2 to the power of 2, where s1 is greater than s2. So if this one is, for example, greater than this one, then we put the s2 here in the numerator and denominator. So the value is there. So then if f calculated is less than f critical from a table, then there is no difference between the variances. But if this is higher, then there is a difference between the variances. Then what we do is that we don't continue on comparing the average. And what we do is that maybe this one, the anodic stripping voltammetry, is the one which I am developing, is generating irreproducible signals. Then I must have to refine it to make it better. So that's the message I get from the f-test. There are, of course, methods of evaluating the average, even if the calculated value is higher also. But in analytical chemistry, I used to, for my students, or even in the future also, when they find themselves being somewhere doing analysis, then it's better to compare to work with the method which is under development to make it more precise. So if the f calculator is less than f critical, which you get from a table, then it's green, meaning that you can compare the average. So you can go and see how this is done. To compare the average, calculate S pooled first. Then this S pooled, then what we say here is that there is no difference between the variances, and it means that I can pull them, I can put them together. So S pooled equal to S1 N1 minus 1 S2 N1 and N2 minus 1, and then N1 plus N2 minus 2. So you calculate the S pooled, and then finally then you can calculate the X, the T decalc. X1, the average right here, and then when you have calculated the S pooled, then you put it here. Remember that this is squared, but this is yeah, the root of this one. And then N1 and N2, they represent the number of measurements done for method 1 and method 2. And this is average for method 1, and this is average for method 2, the absolute value. So if T calc is now less than T critical, which you get from a table, and then there is no difference. There is no difference between the methods. So now what this means is that I have succeeded with my method. My method is as good as the well-established one, at least for the analysis of the analyte which I was looking for now, copper, for example, in water. And this is number 2. And then number 3 is comparison. Also comparison using T pair. Okay, and then this is done using, let me see, here, I can give you an example. Let's assume that we are looking for, yeah, this is water sample, and then we want to measure on iron, copper, lead, cadmium, and so on. Iron, lead, copper, and cadmium, for example. And this is using method 1, and then this is method 2. Let me see, method 1, and then method 2. Let's say that we get 100 ppm or ppb here. You can say ppb there also. 100, 98, 30, 250. And here we have 98 maybe, and then let's say 100, 29, 145. So what do you say now? Can we do the same way as we did before? Just take the average and the standard deviation in a similar way as we did here, or not? This is what we did when we compared 2 sample means. And now the question is, how should we proceed here? Can we do this? Can we do it the same way? No, we cannot, because it will be like mixing cats and dogs, because we are measuring on different things: lead, cadmium, copper, and iron. So what we do here is we pair them. We talk about delta 1, delta 2, delta 3, delta 4, and so on. And we take the average, yes, and then standard deviation for the average. the standard deviation for these differences. Average of differences and the standard deviation for the differences. And we can, from the expression for confidence interval, this was what we had for the confidence interval, and this was what we had for comparison of a mean with a known value, t-calc. And here what we have is then the average of the differences, and then number of differences, and then standard deviation of differences. Oh, standard deviation. Sorry. Must have to. Okay. But I understand what this is standard deviation for the differences. So if the t calculated here, if the calculated value is less than the calculated value is less than the table value, then there is no difference. No difference. Also, no difference between the methods, method 1 and method 2. And why we pair now is because we are measuring different things in the sample. And the pairing can be done also if we have, for example, a site which we sample on. We can take a sample from here, and then we can take a sample from there. We can take a sample from there and there. And even if it's the same element which we are measuring on, let's say it can be lead, for example, in water. So the concentration of lead here can be much more higher than what it is there. So in this case, the different samples here, they must have also to be paired if we are going to compare two methods. So the pair t-test is done when you have a sample that contains different analytes, chemical compounds, which we need to measure on, or if it is a site where we sample on, and then the concentration of the analyte can be different based on where we take the sample from. In this case, you must have also to pair. And another way of another example of pairing is also if there is something which varies with time, like let's say that we are going to check the concentration of alcohol during fermentation, for example, day 1, day 2, day 3, day 4. So the value can vary from day to day. And in that case, you must also have to pair the results. Okay, then we have talked about this. Then I can go back to my PowerPoint. Okay. So, do you see that? Am I back?
Yes, we see your slides.
Good, nice. So this is a table for the F-test. If you have two methods to compare, then the first one is the for method 1, and then in the row, that's the horizontal one, and then the vertical one is for method 2. Then if you have, for example, 7 measurements there and then 7 measurements there, then you can 7 degrees of freedom in each, 7 there and then 7 there. And the value will be 4.99. So what you do is that you compare this value with the value which you have calculated. And if the value which is calculated is higher than this one, there is difference. If it is lower, then there is no difference. Okay. So this is just what I went through on the whiteboard. I did it so because it will be much more clearer than just to show you the slide here. When two sample averages are to be compared, one asks if the difference in the average is significant. So here we are talking about two processes, process A and process B, and then we have a difference of 1.30 between the two processes. And then we have the average for process 1 and the process A and average for process B. So is there a difference between these results? So we must have to to go through F-test and then T-test. And we have sort of null hypothesis. This is like the devil's advocate. There is no difference between the methods. Let's assume that we are, sometimes it can be good, sometimes it can be, I mean, it depends on what type of problems we are dealing with. Let's assume that we are dealing with organic synthesis, and then we want to increase the yield from 65% to 75 or to 80%. And then we change the catalyst, for example, in the reaction, in the organic synthesis. And we want to check if 75 is higher than 65, if it's by coincidence or if it is a real difference. And then in that case, we must have to prove against the null hypothesis. The null hypothesis says that there is no difference between these two averages. So an assumption is made such that the two series originate from the same population and that there is no difference between the two methods. This is known as the null hypothesis. We test this hypothesis against an alternative hypothesis, that is, there is difference. By doing so, we can calculate the probability of finding the difference by chance. If the null hypothesis is right, then there is no difference between the averages. So it depends. In the examples which I showed you, we were working with method development, and then we want to get the same result as a well-established method. For example, when we are doing some method development for analysis of something, then in that case, then we want to prove that the null hypothesis is valid. But if we are doing some synthesis and then we want to increase the yield, then we must have to prove against the null hypothesis. And this is the average or the summary of what I showed you on the whiteboard. Comparison of an experimental mean with a known value. This is the first case, and comparison of the two means of the means of two samples. Do F-test first. If the F-test shows no significant difference between the two variances, continue with T-test. Calculate a pooled estimate of standard deviation. And then pair T-test. And then you must have to know when to do the pair T-test and then when to do the comparison of two means. Pair T-test it's when you have different analytes in the same sample, or if it is the same analyte but taken from different sampling sites where the concentration can vary. And then the pair T-test is calculated using this relationship. Okay, then that was it when it comes to the first part, and then a short note only on the calibration. Let me see. Here. Whiteboard. Now I am back to the whiteboard also. Yeah, good. Okay. Determination of concentrations. Analyte. By analyte, we mean if the sample, for example, it can be blood, it can be water, it can be nail, it can be hair. So the analyte is the chemical compound which you are looking at in the sample. So what we do here is that we prepare standard solutions, standard 1, standard 2, standard 3, and so on. And then we have also our sample. And then we have our blank. A blank is something which goes through the whole sample workup or the sample preparation steps. It can be water, for example. If you are dealing with blood, then you can take, for example, 5 milliliters of blood, then or blood serum. Then you can have a blank of some sort of a buffer, for example, as a blank. And the blank should not contain the analyte of interest, but it should go up the same steps as the sample. So hopefully then you will get a linear relationship between the concentration of the standards. This is standard 1, 2, and so on. Then what you do then is you go with the signal which you get for the sample and then read the corresponding concentration on the x-axis. And then you do the same with the blank, go into the calibration curve and read the corresponding concentration in the blank. Most of the time, the blank should not contain the analyte, but you can have some sort of contamination in your analytical procedure in the sample treatment steps. So you can get some contribution from contamination. So then you must have to subtract this value from this. So this is good. If you have, let's say, 10 samples, then you can measure on the 10 samples and then use the same calibration curve for all the 10 samples. You just go in and then read, the corresponding concentration on the x-axis based on the sample, on the signal for the different samples. So this is what we call external calibration curve. Yeah, so there is a limitation here. Most of the time, we have something in the samples that complicates the analysis. So it's straightforward to analyze, to determine the concentration in the standards, to measure on the standards. But when it comes to the sample can contain, something that can complicate the availability of the analyte for the detector. So something is masking, something is interacting with the sample, or the sample is decomposing, or the oxidation state is changing. For example, arsenic 3, arsenic 5 can get reduced to arsenic 3 or the other way. So if you are doing some sort of speciation, so a lot of things can happen. So this external calibration curve then will not be enough. So what we do then is a standard addition. And here, what we have is our sample everywhere. This is a sample. Oh, sorry. So let me see. So it's a sample. The sample is everywhere. So we add to the sample spikes standard 1, standard 2, standard 3. And then here we don't add anything, it's 0. Let's assume that we are adding 10 microliter of increasing concentrations of some aluminum, for example, can be aluminum in baby food, some sort of baby food. And we add, let's say, 10 ppb of aluminum, and then 20 ppb, and then 30 ppb. But here we have the same volume, but not, let's say, if the volume we are adding is 10 microliters, so I add 10 microliters of water only. So no standard here. And then we have a blank, not the sample here, blank. So what we do is then we subtract the blank value from each measurement here before we plot the signal against concentration. Signal. And not very, very important here is added concentration. This is not the absolute or the absolute concentration in the sample. Added, that's what we know, added concentration. That is, this can be 10 ppb, 20 ppb, 30 ppb, and so on. And remember also that the sample, it contains, if it's aluminum we are looking for, it contains aluminum. So when 0 is added, then we are here. Then we will have a value there. And then after the first standard addition, this is standard 1, and then the second standard addition, and then third. Then you will have an extrapolated value here on the minus side. So this is the concentration of analyzing your sample, just evaluated by extrapolating this backwards. And if you parallelly move this line now, so that it passes origo, just you can think of getting this on the positive side, but you don't need to do this maneuver either. But this is just to show you, to compare this with what we had earlier for the external calibration curve. So you can read the same value on the positive side. So this value and this value is the same. Just this is on the negative side, but you can just take out the minus, and this is a value in your sample. So now, how do we know? Should we go for the standard addition method, or should we go for the external calibration curve? To mention here, if we have, let's say, 5 different samples, then you must have to make 5 different standard addition curves. But here, if I have 5 different samples, then I can use the same external calibration curve, because this is independent of the sample. These are standard solutions which I take from the chemical store and prepare these standard solutions. But here it's spiked, the sample is spiked. You have sample here, and the sample you add standard 1, standard 2, standard 3, and so on. So this will lead that you will need more time, because you are going to have, if you have 50 samples, then you must have to make 50 standard addition curves. So this is very time consuming, but exact, you can get exact value, because all the points are subject to the same error. So in this way, then we are not discriminating the sample of the analyte, because they are in the same metrics, so to speak. So standard addition, this is used when you have matrix effect. In the analysis. So how do I know if I have matrix effect or not? Then what I need to do is I must have to do it in both ways first, using a standard addition method and then using the external calibration curve. And then if this line, if the slope of this line is the same as the slope of this one, then I don't have any matrix effect. So after parallelly moving this line so that it passes origo, this line is exactly the same. If I don't have any matrix effect, it's exactly the same as this one. Okay, so if the lines are parallel, then I will be happy, because I will use this external calibration curve for my 50 samples. But if the line is, if the lines are not parallel, if the slope is changing, then I must have, to do 50 different calibration curves. This is what we call standard addition. And then there is a way of circumventing this problem in some way. If you are a good analytical chemist, or if you can work with your sample, then you can have something which is something in between. I will call it matrix matched calibration curve. And matrix matched calibration curve, it's simply that you have one of the samples that contains very, very low concentration of the analyte, close to the blank. If you have such a sample that does not contain the analyte but the matrix only, then you can make the preparation of the calibration curve not in water or in a buffer, but in the matrix. Then this is what we call matrix matched calibration curve. So this contains the matrix and then it's prepared in the matrix. So standard 1, standard 2, standard 3, and so on.
Professor Tesfalidet, I'm sorry for interrupting you, but we have only 10 minutes.
Yeah, I'm done now.
Okay, thank you, because maybe somebody will have questions. Exactly.
So this will be like the first one, So that was, you came in at the right times. So that was the last 3 different ways of doing the calibration curve. And also one thing to mention here is that in doing linear regression, you assume that all the variation you have is on the y-axis, on the instrument side, on the detection, not on the x-axis. This means that you must have to do to prepare the standard solutions in a very accurate way. Because let me see. This is the final one. So if we just look in one of these points, and this is the fitted line. Then we want to minimize this error, the distance from the fitted line to the individual values here. So it's very important that these concentrations are prepared in a good way. Or if you use, for example, reference solutions, then it's good. But if you prepare them by yourself, then you must have to be careful in preparing them. Okay, then I think that will be the final. That's what I have to say now. I can stop there and then see what type of questions you have and come back maybe to some parts of my slide and so on. Okay.
Thank you very much for this explanation, such a complex material. Thank you for your time. Very interesting. And I guess we have some questions in the chat. Can you see the chat?
Let me see. I didn't have time to go. I was focusing only on myself. Okay, let me see. Why should we exclude it? Okay, so question number 1, I think what you mean here is with experimental error, because it's divided into systematic and random. The random error, we cannot do something to that, but I think you mean here systematic error. If it is systematic error, yes, we must have to make the calibration perfectly, and then we must have to avoid all sources of systematic error. That's correct. But if we fail to do that, then we must have to be able also to see. It can be like a pipette. You have been just to make it simple. You have been pipetting 10 milliliter exactly, close to 10 milliliter all the time. But accidentally in one of your measurements, then you get a big bubble there, but you didn't notice it. Then you get a value which is much more different than the others. Then in this case, then you can see it by using R-test or Q-test. But normally what we do is that we must have to calibrate the instrument perfectly. So it's I hope that it was enough as an answer for that. In what situations should a biologist check his or? Yeah, it depends on what type of questions you have to deal with. What were you thinking about? who posed question number 2? Can you give me an example?
Nikolai, maybe you can join us in the conversation.
Hello. Because I never heard about testing for normality test in biological investigations. I had it first in some more data laden fields of science, but
yeah, normality. What do you mean by normality?
I mean normal correspondence to normal distribution.
Okay, precisely. So normal distribution, precisely. Yeah, it depends on the question, but you can have also some modality. You can have other types of distribution to consider. But now what we have considered is a normal distribution, meaning that we are assuming to have 95% confidence limit, for example, and then normal distribution. But there are other distributions, of course.
Thank you a lot.
Yeah. And then, are there any disadvantages of such information except here, and how to avoid disadvantages of statistical methods? Yeah, disadvantage. That one big disadvantage is that you may think like you are very good in mathematics, in statistics, and then you can correct for whatever mistake you have done experimentally, and that is something that that pops up, every now and then. But despite that, I mean, with exception of that, I think the statistics you needed to have some measure of spread to give a measure of spread in your results. And you have been talking about F-test, T-tests in your evaluation. No, we don't use. We use only this basic statistics as I showed you with F-test and T-test and Q-test.
Okay. Any other questions? Well, our participants start thanking you for the wonderful and exciting lecture, and I'm joining them. Thank you very much. It was interesting. Thank you for joining us in our summer school. We hope to see you next year, if you don't mind.
Thank you. Maybe I can maybe include more biological stuff also, non-parametric parameters, like statistics.
So thank you very much for your time, and I think there are no more questions. So this is it. We can let you go. Actually, have rest after
Thank you.
material. Thank you very much.
Thank you. Bye bye.
Goodbye.
Bye.